Well, I want to do a little explaining of a complicated subject. Okay, what isn't complicated in chemistry? Uh, this is complicated because it involves a couple of curves and activation energies and how things react. In order for something to react, let's look at this stuff. Here we've got two reactants. We've got, this looks like something like HCl. And if it smashes into this molecule, it smashes with enough energy. These things are being crushed together. They are being forced together by a collision. And that's the critical thing here. We'll get back to that collision in a second. If that collision is fast enough, has enough kinetic energy, enough velocity, and mass also for kinetic energy, and it's at the right orientation. You have to have both. You have to have a great collision, and the collision's got to be so the geometry is right. The right substances, the right part of the molecules hitting the other right part of the molecule. You get this sort of transition state here. In fact, actually, this is an OH. And here this OH is smashing into this organic molecule. And kabam, we have this new forced together transition state. Now they could uncome together and roll down to less kinetic energy and separate again, or they could roll down to a lower potential energy. Now this would be an exothermic reaction, which is, I'll get back to this later, thermodynamically favored, because these new products have less potential energy than these originals. So we sort of smash things together. Wow, we've got something better. We've got a new substance with lower potential energy, and we've made our reactants. So we have, these two reactants coming together to make this. You need sufficient kinetic energy to smash together. You have to have the right orientation. And if you're asked on an FRQ what is needed, you need two things to get the successful transition state. And then we end up getting our products. So this is our barrier to getting our products. And the only way you can get up that barrier is with a collision. And collisions involve speed and molecules smashing together. And this is where we get to the Maxwell Boltzmann curve, which tells you about molecules at a specific temperature. So notice I've got a temperature here, a temperature 1, a temperature 2, and temperature 3. Now look at these curves here. Now these curves are sort of a scattergram. They tell you how many molecules have sufficient energy at this temperature. In other words, we've got a lot of molecules with this kinetic energy. And well, this is the energy. And this is the height, is the number of molecules. So if you want this energy, this is how many molecules have this energy. This is how many molecules have this energy. In fact, let me get my little, I've got an arrow here. This is sort of the average. If we look at all these molecules bouncing around, this is the number of them, quite a few, that have this energy. The energy is on this axis. I'm going to go now to a simulation. Paul Fallstadt made this. It's a Java applet. And this is molecules bouncing around. And they have kinetic energy. This is sort of fun to watch. This is at a given temperature. This is a simulation speed. In other words, we have a temperature, Kelvin temperature of, this seems to be arbitrary, 10.3. I presume that's a Kelvin temperature. And even though we have one constant temperature, notice the temperature is 10.2, 10.05. That's what the simulation is. These molecules don't have the same speed. The red ones and the purple ones are the slowest moving. So I'm going to look around to see if I can find a blue one. Here's a blue one moving not for very long, slowly. Here's a purple one moving very, very slowly until it gets smashed by somebody else. And in these collisions, we have, like I say, some collisions result in a karam where things really get kicked off quickly. Sometimes they cancel one another. Keeping track of the molecules here. Here's a track of the molecules. And, oh, I got to pull this up. This is keeping track of the molecules here. In other words, we have this many moving slowly, we have this many moving faster, and we have this many moving fastest. Now let me increase the number of molecules. I can increase the molecules. Let's see, molecule count right here. I'm going to move the molecule count up so we have a lot. We move the molecule count up. In fact, let me move it to, now look what's happening here. We're seeing that here's the slow-moving molecules, here's the moderately moving molecules, and here's the fastest. And this is the average temperature. The average temperature, according to this, is 8.67, roughly. Now let me increase the temperature. I can increase the temperature to 10. And notice this peak shifts over and it flattens out a bit. Let me shift it further. And again, it flattens out some more. Let me get it to a really, really low temperature. And we should have this shift backwards. Gravity is irrelevant in this simulation. So here we can see at this low temperature, our peak average energy. This peak is close to the average. The average kinetic energy temperature is this. But if we raise the temperature, give it some time, our average is right about here. It's further up because we've got a higher temperature. We always have some people who are overachievers. We've got some molecules that are underachievers. So we have this scatter. Not everybody's doing exactly the same thing. That's what the Maxwell Boltzmann curve is. This is a result of random motion. And that's what this Java applet simulates. So let's go back to the three diagrams I had. Here we had one temperature. Here's the average temperature. Here we've got another temperature. Here's where the average is. Here's our third temperature. And here's this average. Now this bar that I have here, this line, is the energy needed to get up here. In other words, this bar, if you have this energy and greater, you can make it up the hill. And at this low temperature, you can see there are not many molecules that can get up this hill with their collision. This is the lower temperature where a smaller percentage of the molecules at this temperature can make it up to here. A few will, and will make some product. Now, if we increase the temperature, the curve flattens out. We get more molecules with high energy. And now the average molecule can make it up the hill. Before, the average molecule couldn't. Now the average molecule can. And even at temperature 3, look, our average is here. Look how many molecules, if they collide, can make it up to this hill. Now, if they have the right geometry, then they'll make the product, or they have a chance of making the product. But at the higher temperatures, there are more molecules, based on the Maxwell Boltzmann curve, that can make this activation energy. So this is the description of how a Maxwell Boltzmann curve that gives the distribution of molecules at a given temperature. At low temperatures, you've got a low average. At higher temperatures, the average becomes further to the right. But the curve flattens out because we always have some underachievers. So always having these guys drag things out. The number of molecules, the area underneath this curve is the same in all of these cases. Maxwell Boltzmann and activation energy.